Hi, welcome back. This is still Ken and we're still on our course on mechanics. And this is the last part of lesson 5 on applying Newton's laws. In the last video, we've been studying about the dynamics of particles, but we did not include yet the frictional forces. In this video, I'm going to teach you about friction, and we're going to include friction in our study of the dynamics of particles. We begin with our study on frictional forces. So oil in car engine, it minimizes friction between moving parts. You usually call this one as your lubricant. But without friction between the tires and the road, we couldn't drive or turn a car. So in this case, friction should be minimized in engines, but we need friction when it comes to driving the car. The air drag, which is the frictional force exerted by the air in a body moving through it, decreases fuel economy, but even if it is, it makes your parachute work. Friction is sometimes a friend and it is sometimes a foe. Without friction, nails would pull out. You cannot actually hammer your nails without friction. And light bulbs would unscrew effortlessly. And lastly, ice skating is hopeless. So even though you think that the ice skating rink is slippery, but without friction, you cannot ice skate on the rink. Now, when the body rests or slides on a surface, the friction force is parallel to the surface. We've already discussed this one on lesson 5.1 on the first part of this lesson. Friction between two surfaces arises from intermolecular forces, and frictional forces are fundamentally electric in nature. Between two rough surfaces at points where they came into contact. What you can see in the image is how your two surfaces come into contact, and the friction arises from the contact between these two surfaces. Now, did you know that smoothing the surface can actually increase friction, since more molecules are able to interact and bond? As you said in the previous slide, friction arises from the intermolecular interaction between your two surfaces. And when there are more surfaces that are in contact, there is an increase in your friction. So the more you smoothen the surface, the more you increase the number of surfaces that can come in contact with another surface, thus increasing your friction. Lubricating oils work because an oil film between two surfaces, such as the piston and the cylinder walls in a car engine, prevents them from coming into actual contact. So if you're going to view here on a microscopic level on the figure, even smooth surfaces are rough and they tend to catch and cling. And if you're going to put some lubricant here, some lubricating oil, perhaps, okay, in between your two surfaces, you are preventing the actual surfaces to come in contact because there is this lubricating film in between your surfaces. And this is how your lubricants work. We have two types of friction. The first is your static friction. This is the force that makes hard things, or that makes it hard to even get things moving. So like say for example in the figure, so the moment you are trying to push something to make it move, the force that resists this movement is your static friction. Okay, and the second type of force is your kinetic friction. This is the friction force that slows things down. So after you going back to the first figure, the moment you are able to start the box to move, and when your box is already moving and you're still pushing, the resistive force now is your kinetic friction. So static friction, meaning at rest, this is the friction that that makes the thing hard to move. And your kinetic friction, it's the force that slows the movement of your body. This static friction, we usually give it a shorthand symbol of your vector Fs. This is the friction that acts when there is no relative motion. Your static friction Fs is less than or equal to your mu s times your normal force. So here your mu s here is the coefficient of static friction. The coefficient of static friction. And here again, your n is for your normal. On the other hand, your kinetic friction, Fk, is the friction that acts when a body slides over a surface. And it usually increases when your normal force increases. So the more heavier a thing is, or the heavier the body that you are trying to slide over a surface is, the kinetic friction also increases. So here, your mu k is the coefficient of kinetic friction. And your n is for your normal force. So these are some of the approximate coefficients of friction for different materials. So we have a column for the coefficient of static friction, and then a coefficient of kinetic friction mu k. So like say for example, we have your steel on steel. When you're trying to, like say for example, slide a steel on another steel, the coefficient of static friction is 0.74 and the coefficient of kinetic friction is 0.57. Your coefficients are dimensionless. Another example is your rubber on concrete, like say for example your wheels on a highway. So the coefficient of static friction is 1 and for kinetic friction that is 0.8. For rubber on a wet concrete, the coefficient of static friction is 0.3 and then the coefficient of kinetic friction is 0.25. So as you can see, compared to a dry concrete and a wet concrete, the coefficient of friction for the wet concrete is smaller compared to dry concrete. Here, your wetting agent, like say for example your water, acts like a lubricant, decreasing the friction between your surfaces. And another important thing to note here is that your coefficient of static friction is always greater than your kinetic friction, or the coefficient of kinetic friction is usually less than the coefficient of static friction for any given pair of surfaces. And in short, we can say here that it's easier to keep the box moving than to start it moving. You may have observed this in some of your activities when you're trying to start pushing like say for example, you're trying to push a cabinet, okay? Starting to or making the cabinet to start to move is actually harder than when the cabinet is already moving and then you're just trying to making it to continually move. So there is this static friction that you need to overcome, and then once your static friction has been overcome, your kinetic friction now acts between your two surfaces. So it's just like doing your it's actually the same concept with doing with your assignments. So or your other schoolworks. So it's usually harder to start your projects, your assignments, than when you are actually now already doing it. So you really need to have this motivation to start something, big motivation to start something, and a lesser one when you're already doing a thing and you're just continuing it. So again, the concept here is that it's easier to keep the box moving than to start it moving. Your coefficient of static friction is greater than your coefficient of kinetic friction. Let's have an example. This is just an easy example. So you want to move a 5 Newton crate across a floor. To start the crate moving, you have to pull with a 230 Newton horizontal force. Once the crate breaks loose and starts to move, you can keep it moving at constant velocity with only 200 newtons. What are the coefficients of static and kinetic friction? So again, you want to move a 500 Newton crate across a level floor. To start the crate moving, you have to pull with a 230 Newton force. Once the crate breaks loose and starts to move, you can keep it moving at constant velocity with only 200 newtons. What are the coefficients of static and kinetic friction? So for this problem, okay, our targets are your mu s and your mu k. But again, from our strategy, what we do is to draw first the free body diagram. So just a rough free body diagram. You have here your normal force. Let me do it again. Okay, so you have here your normal force, and then you have your weight, and this is equal to 500 newtons, and you apply here some force F of uh, of 230 newtons if you're going to move it. So if you're trying to move it, so meaning on the other side there is this static friction that resists your motion. If on the other hand you want to, if on the other hand when the crate breaks loose and starts to move, okay, so we still have your normal force, you still have your weight, but this time you are now applying a 200 Newton force. So since this is already moving, on the opposite side you have this kinetic friction. So our target here is just your coefficients. Okay, let's write an equation along the x. So you have here your by the way, what you see here is you have your constant velocity, so that means this is an equilibrium problem. So along the x we have 230 newtons minus Fs, and this is equal to 0. And along the y you have your normal force minus your weight, which is equal to 500 newtons, and that is equal to 0. So here your friction Fs is equal to 230 newtons, while your normal force, this is equal to 500 newtons. Let me erase this one first, and then let's just redo it later. Okay, so again here, or from your equations, your Fs is equal to 230 newtons and your normal is equal to 500 newtons. But our target here is mu s. So your Fs, this is equal to mu s times n. So your mu s, that is equal to Fs over n. So your mu s, that is equal to 230 newtons divided by 500 newtons. So here your mu s is equal to 230 divided by 500, and that is equal to 0.46. So that is your coefficient of your static friction. So your mu s is equal to 0.46. Now let's find your mu k. If you're okay, let me erase these things. Okay. We can use the same free body diagram, but this time, since you are not talking here about the kinetic friction, the force that you're applying now is only 200 newtons, and on the opposite side there's this kinetic friction that resists the movement. So along the x, the sum of all your f of x is equal to 200 newtons minus fk, that is equal to 0. There is no movement first, or there is movement, however you are moving with constant velocity, so your acceleration is 0. Along the y, we have n minus 500 newtons, your weight, that is equal to 0. So Fk is equal to 200 newtons, and your normals is still 500 newtons. Your Fk is equal to mu k times n, so your mu k is equal to Fk over n. So here your mu k is equal to 200 divided by 500 newtons. Your mu k, that is equal to 0.4, is 0.4. So this is 0.4. Okay, so your coefficient of kinetic friction is 0.40 or 0.4. If you've got a mu k that is greater than your mu s, then perhaps your answer is wrong. You can just you can check it using our concepts of your static and then your kinetic friction. We have this other type of friction which we call your rolling friction. So we can define a coefficient of rolling friction ur, which is the horizontal force needed for a constant speed on a flat surface divided by an upward normal force exerted by the surface. The rolling friction is usually called by transportation engineers as your tractive resistance. Typical values of your rolling friction, like say for example your steel wheels on steel rails, you have 0.002 to 0.003, and then your rubber tires on concrete, that is 0.01 to 0.02. And as you can see, your rolling friction is smaller compared to both your static and then your kinetic friction. That is the reason why in transporting things we usually use wheels to make our work easier, since you have smaller rolling friction. Railroad trains are more efficient than highway trucks because your rubber tires on concrete rolling friction is greater than your steel wheels on steel rails. Another type of friction is your fluid resistance. So this is the resistance that you feel while moving in a fluid. The force that the fluid or gas or liquid exerts on the body moving through it. So when we talk about fluid, we do not only mean your liquid, but a fluid is both a gas or again, a fluid is either a gas or a liquid. So anything that flows, you call that one as a fluid. So it's not a closed term only for your liquid, but it also comprises your gases. By Newton's third law, the fluid pushes back on the body with an equal and opposite force. And for small objects, such say for example dust particles moving on air or ball bearing in oil moving at very low speeds, the fluid resistance F is equal to your Kb, some constant K, and then your velocity. This is fluid resistant at low speeds. Like say for example again your dust particles moving on air, so they're just moving at very slow speeds. And for larger objects moving through air at the speed of a tossed tennis ball or faster, the resisting force, or what you call your air drag, or the drag, has a value of F is equal to dv squared, where your d is uh, some uh, some coefficients for larger objects, or for your drag force. By the way, sharks are among the speediest ocean predators. And why is that so? So if you've observed, or if you have seen in movies, sharks actually swim very fast. And you know why this is so? So this is because of the tooth-like scales of shark skin. So if you're going to take a portion of the skin of the shark, and then you are going to magnify it using a powerful microscope, like say for example a scanning electron microscope, this is what you're going to observe. The Well, your sharks may look, or the skin of the sharks may look like smooth on the outside or on the macro scale, but on the micro scale, this smooth um, skin actually looks like this. It's like tooth-like. So these dermal denticles are ribbed with longitudinal grooves, which result in water moving very efficiently over their surfaces. Also minimizes the collection of algae. So what you can see here is this rough skin of your shark breaks your surface tension more easily, thus making your sharks swim faster. So uh, that's it. So this is the reason why your sharks are among the speediest swimmers in the ocean. So let's have an example involving your friction this time. Uh, Block A in the figure has a mass of 4 kilograms, and block B has a mass of 12 kilograms. The coefficient of kinetic friction between block B and the horizontal surface is 0.25. What is the mass of block C if block B is moving to the right and speeding up with an acceleration of 2 meters per second? What is the tension in each chord when block B has this acceleration? Okay, so let's repeat the problem. Block A in the figure has a mass of 4 kilograms and block B has a mass of 12 kilograms. The coefficient of kinetic friction between block B and the horizontal is 0. Or horizontal surface is 0.25. So what is the mass of block C? Block B is moving to the right and speeding up with an acceleration of 2 meters per second squared. And what is the tension in each chord when block B has this acceleration? So we have here again your diagram, and I have here some terms. So for the chord between your block A and block B, we'll use TAB for the tension between these areas here, and you're going to use TBC for the tension on the chord between these areas here, between your blocks B and C. And note that we always include the direction of the acceleration in each free body diagram for us to be reminded where your systems are, or where your system is moving. So let's draw the free body diagram. So here we have three systems. So since we have, or three systems, we have three bodies. Since we have three bodies, we draw one free body diagram for each. So let's draw the free body diagrams. So for mass A, okay, so the forces acting here are just your tension, TAB, and we have your weight of your mass A. And we include the direction of the acceleration. It goes upward when your block B moves to the right. So this is again for mass A. For your mass B, or your block B, okay, so we have here your normal force, and we have the weight of block B, and to the right we have tension BC. This pulled by a cord to the right, and you also have a cord to the left that uh, pulls your uh, that also pulls your block B. So this is TAB. But when your block B moves to the right, your kinetic friction also acts. So we can add here another friction, your kinetic friction Fk acting on block B. And for mass C, or your block C, we just have your tension BC, and we have the weight of block C in the direction of the acceleration, which is downwards. So next we are going to write the equations of motion. Again, our first step always is to draw the free body diagram. So our next step is to write the equations of motion. So for block A, so along the X, so we do not have forces along the X basing here on the free body diagram, so this is equal to 0. Along the Y, we have tension AB positive plus negative weight A, so this is minus weight A, and then this is equal to the mass of A times its acceleration, which is upward. For mass C, or for block B, along the X, we have your TBC minus your TAB, and then minus FK, since they are on the negative x-axis, and then this is equal to your mass of B, since it accelerates along the X, so mass B times A. And along the Y, you have Fy, so you just have your normal force, we write here your normal for B, minus the weight of B. And since there is no acceleration along the y-axis, this is equal to 0. And lastly, for block C, along the X, this is 0, and along the Y, we have your TBC minus weight B, and then this is equal to minus MCA. We have minus MCA because the acceleration is downwards, so your downwards acceleration is negative. So we have this, we can say 6 equations that we're going to use to solve for. Again, our targets are your mass C, your tension BC, and your tension AB. So let's solve this one. I hope you have taken note of our equations here. So from the first free body diagram for your block A, let me just draw it again. So you have your tension AB, and then you have your weight of mass A, and we have written the equation of motion of this one, which we have just along the Y, since along the X it is 0, so you have Fy, this is equal to TAB minus weight A, and then you have an acceleration upwards, this is equal to your mass of A times your acceleration A. And again, we are given with the following. The mass A is equal to 4 kilograms. So this is 4 kilograms. And your acceleration is equal to 2 meters per second squared. And we can actually solve here if you have if we have TAB, you have TAB minus weight A. This is equal to your mass A times the acceleration. We can actually solve your tension AB, which is one of our targets. So you have mass A times acceleration plus your weight A, or this is equal to TAB, and then mass A times acceleration plus your weight A, which is equal to mass A times G. And you can solve this one, and you'll find that the tension AB is equal to 47.2 newtons. So you just substitute these values here, and can solve for the first or one can solve for one of our target variables, which is the tension AB, and that is equal to 47.2 newtons. So let me redraw again your second free body diagram or second free body diagram. So this that is for your block B. So we have a normal force which is upward, and then you have the weight of your block B, and then to the right you have your tension BC. To the left we have your tension AB, TAB, and then since it's accelerating to the left, we also have the action of your kinetic friction on block B. And we have the following equations of motion. We have TBC, TBC minus TAB minus your FK, and then this is equal to your MBA for your block B, and along the Y we have NB minus weight B, and this is equal to 0. So we can solve here your tension BC, but before solving your tension BC, let us find first your normal force, which is equal to your weight of block B. So this is just equal to your the mass of block A times G, block A, the mass of block B times G. So here, your mass B has a mass of 12 kilograms, and you have your acceleration, which is equal to 2 meters per second squared, and we have your coefficient of kinetic friction, μk, which is equal to 0.25. So your normal force is equal to that is 12 kilograms times 9.8 meters per second squared, and you get a normal force of equal to 117.6 newtons. So from this equation, from the first equation, we can solve for your tension BC. So your tension BC is equal to your MBA plus TAB, and then plus FK. Your FK, this is equal to your UK times NB. So you have 0.25 times 117.6 newtons. So your FK, that is equal to 29.4. That is equal to 29.4. newtons. So your TBC, this is equal to your mass of B, 12 kilograms times 2 meters per second squared, plus TAB, which is equal to 47.2 newtons, and then plus your FK, which is equal to 29.4 newtons. So your TBC, this is equal to 106 newtons. So this is equal to, this is equal to your TBC is equal to 100.6 newtons. Okay, so we have already solved your tension AB, this one here, and you've also solved your tension BC. The only thing left for us to solve is your mass C, the mass of this block here. So to solve for mass C, we can use your third free body diagram. So we have already drawn this one earlier. So above you have your tension BC, and then below you have your weight of C, and it accelerates downwards. So again, we have your equation of motion just along the Y. You have TBC minus weight C, and then this is equal to negative MCA. That is a negative again because your block C moves downwards. It has acceleration that is downwards. Our target here is the mass C. So let's rewrite the equation. So you have TBC, and then you have weight C minus MCA. But your weight C, this is just your mass of C times G, and then minus MCA. So we take out the mass in the equation. So we have TBC, and then this is MC, G minus A, dividing both sides by G minus A. Okay. We have your mass C is equal to TBC over G minus A. So we have here 100.6 newtons for TBC divided by 9.80 meters per second squared minus 2 meters per second squared. And then your MC is equal to 12.9 kilograms. So you have the mass of your block C to be equal to 12.9 kilograms. And we finally solved the three target variables for our problem. Just a last note. Is it better to push or pull a heavy object? You can pull or push a sled with the same force magnitude, Fp, but different angles Q, as shown in the figure. And assuming that the sled doesn't leave the ground and has a constant coefficient of friction M, which is better? Is it better to push the sled with your force Fp, or is it better to pull with a force Fp here? Now let's look at the free body diagram for this one, or let's look at the components of your forces. If you're going to push, okay, so you have this push here, Fp, and you can resolve this one. So we have your Fpx, and then you have here your Fpy. If you're going to pull, so you have here your Fp, and then you can resolve this one. So you have here your Fpy, and then you have here your Fpx. Now what's different with these two forces is your y components. You have here your Fpy, and then you have here your Fpy for your pulling. Now what happens when you are going to push? So remember that in pushing, you have here the weight of this lead or the object. And then if you're going to push, you have an additional force Fpy. And then you have here your normal force. Take note that your Fk is equal to your mu kn. And your here, your normal force is equal to your Fpy plus your weight. So there is an additional force Fpy in your normal force when you're going to pull. If you're going to look at here in pulling, you have here your weight, you have here your Fpy, and then you have here your normal force. So for this case here, your normal force is equal to your weight and then minus Fpy. So you are subtracting your Fpy component to your weight. Thus, it makes it, or it has it has a lesser normal force compared to when pushing your object or your sled. So from that, when you push, there is one component of force that adds to the weight of the body, and hence there is more friction. When you pull, the vertical component of force is against the weight of the body, and hence there is a less overall friction. So it is easier to pull than push an object. But of course, this is only the case when you have your forces that is projected at some angle. If you're going to push and pull just in the horizontal, just a horizontal push or pull, there is no component that adds or is against your weight of the body. So in this case here, the push and pull is the same. But when you push and pull at some angles, it is easier to pull than to push. Okay. So now you know that it's better to push or pull a heavier object when you are pulling or pushing at a certain angle. So that's it. This is the end for lesson 5. And just a quick review. In this lesson, we applied your Newton's law to particles in equilibrium and also to the dynamics of particles. And we have discussed the types of friction and included friction in our study of the dynamics of particles. So that's it, and thank you for listening. See you in the next lesson.